Hi, I'm Mr. V, and today's lesson is about from the illustrative math curriculum lesson. It's a unit 2 on congruence, and this is lesson 13, which is about proofs about parallelograms. And it's very involved. We'll talk about it here in a moment. First, I'd like to go through a couple of the homework problems. So this is one of the problems, and if I were you and I were doing this, I would try to follow a similar path as to what I'm going to show you. I'm going to draw each of the triangles to make sure I understand them. So we have ABE and DBE. To do ABE, I'll do this like here. ABE would be this triangle, and triangle DBE, which I'll do in a different color, would be this one. And there is not enough information to show that these two triangles are congruent. This is not enough. Next, we look at triangles ABD, and I'll do that in this color, ABD. Pen tool. ABD is this one. And is it congruent to DAE? DAE is going to be here, DAE. And notice the letter order is important, but here it doesn't matter because these are not congruent. There's not enough information to show that without a doubt that in this isosceles trapezoid, these are congruent. Here we have ABE, and we have triangle BAD. Well, here I have a side that's congruent to this side, and this side is congruent to itself, and my large angle here is congruent to my red angle over here. I should do that in red. Try to do it in red. So you see by the side angle side triangle congruence theorem, these two triangles must be congruent. And I'll color them in like this. Now let's look at the next one. Here we have triangle A, starting with this point, ED. And we're going to look at triangle BDE. And I'll do it in a different color. Triangle BDE. And again, I've got a side. I've got a common side here between the two triangles. And I've got this angle, which I'll mark in blue, and this other angle, which I'll mark in red, are congruent. So let's say I'll mark it in red. I've got to change my colors, red. And so you can see that these are, by the side angle side, these two triangles are congruent. And yes, there is enough information to show that they are congruent. And finally, this is from the homework. And this is the way that I would go through this, because when you see this on a test, you don't want to just guess and just look at it. You want to actually draw it and draw it out, because that will help you. Triangle EAB, which is right here, and triangle EDB, this one. And no, these are not congruent. There's not enough information. Let's see. Match each conjecture. So each one of these, this one here is a conjecture with the rephrased statement of proof. So in the conjecture, we give this general idea, but when we write it as a proof, we usually have a given and a prove statement. They say in this, and they started show, and that's the same idea. I would prefer to see given blank, prove blank. So here we have given, if the diagonals of a parallelogram bisect each other. So what you're trying to prove is that EG would bisect this and make these two congruent, and HF would bisect this, making these two segments congruent. That's really what we're trying to prove, is that these two segments and these two segments are congruent. Those two, the two pairs are congruent to form a congruence. But we don't know that. What we do know is that it's a parallelogram. And you can mark on it, what do you know about a parallelogram? They could have said it's a parallelogram with EF parallel to FG, and with, I'll do this in a different color, with HG parallel to EF. They could have said that. Instead, they just say in quadrilateral EGF, FGH. Here, they're not even telling you it's a parallelogram. Lesson number 2 says in parallelogram, they show this is congruent. One person said to me that it was number 3. And we're told that in the quadrilateral, that EK is congruent to GK, HK is congruent to FK. And then we were supposed to show it's a parallelogram. But notice, that's not what this is saying. What this is saying is that the diagonals of a parallelogram is what's given. So if you're given a parallelogram, show or prove that that EK is congruent to GK and HK is congruent to FK. That's what you're trying to prove, that last part. So this actually is a statement of the last one. The third statement is what do they call this? The converse. And I'll point out to you that if we have a statement, if we say if this, then that, the converse of this is the converse. It switches the arguments. So it would say if that, then this. So for example here, if we have a quadrilateral with EK is congruent to KG and FK is congruent to HK, then EFGH is a parallelogram. Well, in this one, if EFGH is a parallelogram, then, so we switch the arguments. And we use, instead of saying if and then, in our arguments, we say given and prove. This is the hypothesis. This is the conclusion. So our last one, which of these always proves it? And if you don't have this written down, you should write it down. We have valid triangle congruence shortcuts, and we have invalid shortcuts. And there are 5 valid shortcuts and 2 invalid shortcuts. We're going to list them as we have the side, triangle congruence theorem, side, the angle, side, angle. The angle, side, angle was the first one that we proved. We also have angle, side, which if you know 2 angles of a triangle, you also know the third. So this is really just that one. And then there's one that is sometimes true, and that's our side, angle, sometimes. It is not always true. So this one would not be valid because it has to always prove it, but it is sometimes true. What are the conditions for it to be true? If it's a right angle that is given, and I'm giving you 2 sides, well, the right angle will always form one triangle. We used to call this HL for hypotenuse leg, but there are other conditions that make it true too. What if the given angle is obtuse? If the given angle is obtuse, then this is also true. In fact, if it's an acute triangle, acute angle that's given, and I'm giving you the longer side is opposite the angle that's given, this is only one place it could be. The problem is it's not unique. It's what is the word I'm looking for? It's confusing. We don't know which one is which. If it's somewhere less, if this is an acute angle and the opposite leg is shorter. And here's an example of that. If I have an angle and this is shorter, it could be here or it could be over here. Isosceles triangle is a good example of it. If I have these 2 legs that are given in this angle, the third side would have to be shorter than those 2. And do you notice that these 2 triangles are not congruent? So invalid would be the ass backwards or the donkey theorem, SSA. And also sometimes it's valid, but not always. And the other one is angle. Why is angle invalid? Because if I have 2 triangles that have the same angles, I could have them be like this, 3 angles that are congruent, but the 2 triangles are not congruent. Why? Well, because one is going to be larger than the other. This is a dilation. This is similarity, and this we will discuss the last part of this trimester. So let's go on with our lesson. By the end of the lesson, you'll be able to prove theorems about diagonals of parallelograms. And so here's something to notice and wonder. What students said was they noticed there are 2 of them that are green. One is a parallelogram and one is a rectangle. That's what I told you too. One has a point on the inside and the other one has a point on the inside. Someone said there's 2 lines, and I want to point out there's 10 segments, not just 9. There's 4 on the side. There's 1, 2, 3, 4, and then the long diagonals is 1, 2. So that makes 10. There's 10 segments. But someone said that there was 2 lines coming from the points. Well, And I think that what they meant was that when there's 2 points, I'm not sure what they meant, because from this point, there are 3 segments coming off of it. From all of these vertices, except for this middle point, there are 4. So a few things to wonder. The pertinent things that people wondered were, I wonder if the diagonals bisect each other. And I wonder if the diagonals of a rectangle are congruent. And we are going to investigate those today. So how could we rewrite this conjecture to make it into a proof kind of statement? The diagonals of a parallelogram bisect each other. And in fact, after you explore and try to do this, if you look back at our homework problem, that's what they did here. The diagonals of a parallelogram bisect each other. This is from the homework. And the way that we did that was saying, given a parallelogram, EFGH, and I would also add that given a parallelogram EFGH such that EF is parallel to GH, EH is parallel to GF, and EF is parallel to HG, show that EK is congruent to GK and HK is congruent to HF. Because if these two are congruent, if EK and GK are congruent, that means that HF is the perpendicular bisector of that segment. If HK and FK are congruent, that means that EG is the bisector of that segment. And that's what we're trying to prove, is that the parallelograms, the diagonals bisect each other. But being specific like this draws it into something that we can actually prove. So we're going to make a conjecture. We think that it's true, and we're going to explore it with this GeoGebra activity. And after we explore it, we're going to find 2 different ways of solving it. And then we will talk about information that is needed, and then I'll go into this page, actually write a proof. I'm going to show you in this video what I did, and then we'll go on from there. So if you look at the GeoGebra activity, to make a parallel line, I'm going to use the parallel line tool. I'll draw it parallel to this segment through A, which means that where they intersect, we will call D. And when I drag each of these points, you can see that it stays as a parallelogram. Each one of these maintains it. But D cannot be dragged because it's fixed. And then there's A. And I can make a polygon out of this. So it'll be A, B, C, D. Notice they go in clockwise order if I'm going to call it parallelogram A, B, C, D. And I'll change the color of this to green. I'm also going to use the segment tool to make the segments from B to D and from A to C. Where they cross, I'll call that point E. So this intersection point we'll call point E. And now, how do I know that they are congruent? Well, I can look at it and I can examine it. I can drag it some more if I wanted to and see what happens here when I drag it. Or I can also, with the GeoGebra, I can measure the distances. So I can measure the distance from B to E, from D to E, from E to C, and from E to A. And you'll see that there are these do, in fact, bisect each other, and you can prove it to yourself. So you can explore this. Then you would write down the things that you needed, how you would, maybe you're going to do this with what we've talked about with triangles. I'm going to show you the way that I would do it with triangles. First of all, I'm given that this is a parallelogram. So that means that the opposite sides are parallel. Both pair of opposite sides are parallel. And I'll mark those. That's what's given. And that the diagonals bisect at X. So we'll label that X. Now we know from our parallelogram theorem that the opposite sides of a parallelogram are the same length. So I'm going to mark this because the opposite sides of a parallelogram are the same length. We also know that a transversal crosses parallel lines. So if these 2 lines, this one and this one, are parallel because it's a parallelogram, and I have a transversal that crosses it here, the alternate interior angles formed by a transversal crossing parallel lines are congruent. This is my alternate interior angles theorem that says if I have parallel lines, then the alternate interior angles are congruent. And I'm going to use that a second time with this diagonal. With this diagonal, my alternate interior angles are this one and this one. And now you can see I have 2 congruent triangles. Why? Because of the angle here, angle here. I have a side. I'll do this in red if I can get it to be red. Side and side. and I have an angle over here. And by the angle side angle shortcut, this is triangle congruence theorem, these two triangles are congruent. And since they are congruent, the corresponding parts of congruent triangles are congruent, which means that this side has to be the same as this. That means that BD bisects this segment. It also means that by the CPCTC, these two triangles, these two sides are congruent, which means that segment AC bisects segment BD. Therefore, in any parallelogram, the diagonals bisect each other. Wow, that was a mouthful. Now, in our synthesis of this lesson, there are things for you to read. You can read this student explanation, and then you should read it, and you should also read this one. This one, they use a rotation, which is a little bit more complex, a little bit different. I like it better with just the one, but there are different ways of proving these, and you can read this on your own. You should. Here, we're going to work backward to do a proof. And we're going to do this. So we're given ABCD as a parallelogram with the diagonals that are congruent. So AC is congruent to BD. We want to prove that this has to be a rectangle. That is, that all four of these main angles, A, B, C, and D, are right angles. And we're going to work backward, starting with this sentence. I would know ABCD is a rectangle if I knew, and then we're going to work it backwards. And I'm going to show you my conversation. We would know ABCD is a rectangle if we knew that all of the angles are the right angles. So I could write, this is a right angle, this is a right angle, this is a right angle, and this is a right angle. Then we're going to say, I would know that all of these four right angles are right angles if I knew that angle D and angle C were right angles, because in a parallelogram, opposite angles are congruent, so that would make this true. I would know that this angle is 90 degrees and this one is 90 degrees if I knew that these two angles were congruent. So I would know, if I would know that these two angles are congruent, then I could tell that they are. And I'm going to say that they're congruent. If they are congruent, then I know that they're 90 degrees because same side interior angles are supplementary when formed by a transversal crossing my parallel lines, okay? So if I knew that they were congruent, I would know that they both have to be 90. Still working backward. I would know that they are congruent if I knew that this triangle was congruent. Let me mark it here, nice. If I knew that this triangle was congruent to, and I'll do this in a different color, let's see, maybe blue, this triangle. So if I knew these two triangles were congruent, then by the CPCTC, the corresponding parts of congruent triangles are congruent. I would know these base angles are congruent. If I knew, I would know that these two triangles are congruent if I knew one of the shortcuts was true, such as side, side, side. Now this one's going to be a little bit more tricky because I have to show three things. First of all, the opposite sides of the triangle are of the parallelogram are congruent because we've proved that opposite sides of a parallelogram are congruent. So that's one. Number two, this side is congruent to itself. Why? Because of the reflexive property. And then finally, we have this side is congruent to this side because it was given. So I know that these two triangles are congruent because of side, side, side. And I think that does the proof. Let me show it to you in forward motion. So going, instead of working it backward. So given parallelogram ABCD, in fact, I'll do it without the markings, and I'll mark them as we go, so maybe it'll make it clearer to you. Given parallelogram ABCD with, opposite sides here are parallel, and diagonals A, C, and BD are congruent. So I will mark this drawing like so. This is parallel, parallel. This is parallel to this side because it's a parallelogram. And this side we're given is congruent to this side. We're supposed to prove that this is a rectangle, which means we have to prove that all four of these angles are right angles. Now I'm taking what we did just a second ago, going backward, I'm going to bring it forward, which is something you have to do for the exit ticket today, for the cool down. So since I know these are congruent, I also know these sides are congruent because the parallel lines, a parallelogram, opposite sides are congruent. That's a theorem that we proved. I know that this side is congruent, and I should mark that with 2 ticks because I've got these marked with 1. This side is congruent to itself because of the reflexive property. A side can be congruent to itself. So I have this triangle with a side, 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 and I have this triangle with this corresponding side, side, side. They are congruent because of the side, side, side triangle congruence postulate. And then since they are congruent, I can mark this angle would be congruent to this angle because the corresponding parts of congruent triangles are congruent. Now, since these lines are parallel, these 2 angles have to be supplementary. And since they are congruent to each other, they have to be right angles. And since they are right angles, in a parallelogram, the opposite angles are congruent. We've proved that. So now I know that all 4 angles are right angles. This has to be a rectangle. And I hope you followed all of this. This is a whole lot. It's a big mouthful for me to say. We could also do more proofs like this with rectangles, with rhombus, squares, the diagonals of these. Now, do you remember the word converse? Converse means if it's a reversing the argument. So if this, then that, instead it's if that, then this. So for instance, if we proved earlier, if a quadrilateral is a parallelogram, then the opposite sides are congruent. Yesterday we looked at this and we said, well, is the converse true? If opposite sides of a quadrilateral are congruent, then it is a parallelogram. You can't just assume it because it's the one way, it's the other. Now check out these 2 statements. A quadrilateral is a parallelogram if its diagonals bisect each other. A quadrilateral is a parallelogram if and only if its diagonals bisect each other. You should put these in your own words and type it here. Now, these IFF, if and only if, and that's the abbreviation for it, IFF, it's a Scrabble word, it actually works. It means that it is a biconditional. It's true in both ways. And sometimes you can have non-examples which don't work in both ways. Sometimes you have the ones that do work in both ways, in which case it is a true if and only if statement. So for example, a person is a parent if and only if they are a mother. Of course, this isn't right. It could be a father as well. So that's my counterexample. This is not an example. This is a non-example. If a person is a vegan if and only if the person doesn't eat animal products. If a person that doesn't eat animal products, a person is a person who doesn't eat animal products if and only if that person is vegan. You see how it works both ways? It's biconditional, and it's one that works both ways. A person is smart if and only if the person is a girl, and this is not a good example. Because it could be a boy, you know. So you can use this with your ideas of quadrilaterals. You know, for instance, a quadrilateral A quadrilateral is a parallelogram if and only if the opposite sides are congruent. Instead, we could say a quadrilateral with if a quadrilateral has opposite sides congruent, it is only if and only if it is a parallelogram. So you could reverse the arguments. Anyway, for the cool down, I want you to do the proof that I just did, and you're going to work it, instead of working it backward, you work it forward. This just shows you an approach to doing this. And by the way, here's the spoiler alert. This is it written out for you in step-by-step what I would do going backward. Your task is to write it going forward instead of going backward. And there is a lesson summary. I know this is a long video, worth watching. Good luck and success.